Hi everyone, my name is Scott Colmar and I'm the lead engineer of the Atomic Aggies, and this is our video submission for the 2021 Spaceport America Cup. Our goal this year was to compete in the 10K COTS category, competing with an air brake system which would be used to supplement our apogee so that we were able to get closer to our 10,000 foot goal. To accomplish this goal, our team is broken down into various sub-leads including manufacturing, recovery, and special projects. Our propulsion team is dealing with the SRAD development of a hybrid motor, and our NAR leads are charged with helping new members get their NAR certifications as well as becoming familiar with high-powered rockets. The various team leads will be going through their individual responsibilities, but from an overall view, our year was relatively successful, all things considered. We were able to conduct a test launch of the air brake system, albeit losing a majority of our airframe components due to a failed parachute recovery. Albeit in a normal context, we would have enough turnaround time to create a new airframe in time to compete for competition. This option was forgoed in the case that the competition was virtual, and a summer test launch would have no bearing on how we placed in the competition overall. I'm going to now hand things over to the various sub-team leads.
Hello, everybody. My name is Benjamin Gross. I'm the manufacturing lead for the Atomic Aggies this year. I'm in charge of building each section of the rocket and making sure the whole thing comes together as one final vehicle for launch. We use composites for a variety of reasons on the rocket. The first reason we use composites on the rocket is because they're lightweight compared to a lot of other materials. Being lightweight allows us to use a smaller motor. The second being it's relatively easy to work with as a team like us. As you can see, we're able to wrap tubes rather efficiently. The third being cost. Composites are not necessarily the cheapest option, but when it comes to our ability to manufacture them, it's going to be cheaper than a lot of our other alternatives. To manufacture our tubes, we use an acrylic mold that we wrap carbon or fiberglass, whichever tube we're making, around a certain number of rotations while infusing and laminating the layers of the composite material together. We then wrap this in a material we call ripstop, which allows us to, in a sense, vacuum seal and get out all the bubbles and spaces in between the layers to give us a real nice, clean lay and strong composite tube. We use that process for both the carbon fiber and the fiberglass tubes of the airframe. Similarly, when we're making the nose cone mold that we apply a release agent to, and we lay pieces of fiberglass throughout the mold, and then we're able to sandwich the mold together with those layers of fiberglass adhering to one another, and then we fill that mold with flour to compact and do the same thing as the ripstop would do for the tubes.
My name is Alex Binder, and I am the recovery team lead for this year's competition rocket. I'm going to discuss this year's deployment system setup. We have a dual deployment system that we utilized with the drogue chute deploying at apogee, and then the main chute set to deploy at 1,200 feet to eliminate drift. Some of our previous years, we've been working with black powder for these deployment systems. Over this time, we've discovered that there's been some pretty major drawbacks with it. The first being the safety issue. Black powder is very volatile, and so it's very difficult to handle, and it's also becoming increasingly difficult to come by. Another drawback of the black powder is that it's very messy. And so it requires a lot of work to be able to clean out the rocket in order to have it ready for another test or another launch. We began looking into CO2 deployment systems as a way to replace the black powder for this year's rocket. We started looking into the development of the CO2 back in December to January-ish and began some preliminary tests back in January and February. We began looking into the CO2 for a few primary reasons, that being kind of the ease of access of CO2, its cleanliness, sustainability, and just the overall safety of it. CO2 is readily available at any stores. It's a lot cheaper than black powder, and it doesn't require any of the hazmat explosive licenses and care that you would need to take with black powder. Some of the deployment tests, we had a few issues with the separation of the stages. We wired the redundant and main systems to be operated off of a single pull pin switch for ease of arming while we were on the launch pad. The performance of the CO2 system itself, we found that it was just about flawless. It pressurized the airframe sections as needed and got the sections separated at apogee and at the 1,200 foot main chute deployment altitude. We didn't have any issues with that. However, during our test launch, we did not pack the main parachute quite correctly. So when the CO2 system deployed, everything separated fine, but the main parachute snagged on the way out and was not able to fully deploy, resulting in a loss of the rocket.
My name is David Moreno, and I'm the project lead for the Special Projects Division, focusing on the development of an air brake system. All right, the purpose of creating the half-scale model or the air brake system in general is that with the purpose of reducing the rocket's velocity to better reach our target altitude. So for example, if we put a more powerful motor in and we have to balance out the weight of the rocket, we can adjust the air brakes to deploy sooner or later instead of changing the weight of the rocket or changing the power of the motor, which just makes things a bit simpler. Brake system functions by using 3 servos connected to 3D printed flaps that deploy at a predetermined altitude using onboard sensors, barometers, altimeters, and we figure out what altitude the flaps need to deploy at using a MATLAB code, which is again predetermined based on the altitude we're launching at, wind speed, temperature, stuff like that. Due to a delay in shipping and time constraints, we had to scrap the idea of using custom-made PCB boards that would utilize all the sensors in a very compact design for the competition rocket. So instead, we went back to the half-scale models electronics, which had a custom 3D printed PCB board, which utilized some of the sensors. And we also added a proto board that would allow the servos to connect to the electronics. Even with some small setbacks, the air brake system was able to deploy successfully, albeit with a small delay due to a timing error in the code. However, with data provided from the avionics system, we were able to find out that the air brakes did indeed create drag on the rocket, therefore reducing the altitude and velocity of the rocket. With the data provided by the onboard avionics system, we were able to confirm that the rocket did indeed reduce its velocity due to the air brake system. This was the original plan we had hoped for. For future generations and iterations, with a custom printed PCB and a few other modifications, we can expect even greater results with the air brake system.
The location and materials used within the air brake system were determined by a number of things. The location was determined by the fact that we weren't sure how much the air brake system was going to weigh, and so therefore we tried to locate it as close to the CG as possible, because a variance of 5 pounds could severely throw our stability margin off. The material, 6061 T6 aluminum, was chosen due to that it was well available, inexpensive, and easy to machine and work with in our machine shop. This way we had a strong structure that was financially viable as well as logistically available. For the more complicated geometries like the flaps, hinges, and pins they sat on, we chose to opt for a 3D printed material due to the fact that it was, once again, easy to work with and all it took was just a simple CAD model to create and print.
Hello, my name is Thomas Wilkinson, and I am the Payload and Avionics Lead for Atomic Aggies. This year's avionics system was designed using 5-volt power and logic, with the exception of the 3.3-volt Zigbee Pro used for live data transmission. The system was comprised of a sensor suite consisting of an inertial measurement unit, altimeter, GPS, which also provided speed, time, and altitude, SD card writer for data logging, and the aforementioned Zigbee Pros. The avionics system is made up of two separate systems, the black box section consisting of all the sensors and data logging, and the transmission and activation section. The idea being we would send a signal from the ground station and arm the black box side when ready to launch to conserve battery and allow full control of data collection and logging. In addition, we had the intentions of also using a Big Red B 70cm APRS GPS for the test launch as well, but sadly had a damaged GPS module. The design process of the avionics system started with a visual fritzing diagram and testing of each sensor individually. Then we moved on to developing our own PCB that the sensors and microcontrollers would attach to. Sadly, we had some issues with the PCB and resorted to neatly breadboarding the system for the test launch. As for the payload, the decision was made to forego the construction of a payload for the test flight as the competition had gone virtual and the team felt prioritizing the avionics section and air brakes was much more advantageous. Prior to the test launch, we had tested the line of sight range we could expect to receive live data from the rocket, which ended up being about 2 miles. Overall, the test launch went great for the payload and avionics team, where we successfully remotely activated our system, received data all the way up to apogee and just prior to landing with minimal packet loss, and got fairly accurate data with our altitudes matching the other altimeters aboard the rocket and the GPS leading us to within 1,000 feet of the final landing location.
In conclusion, there are a few things that we would of course fix about this year's vehicle. The first one being that we would adjust the air brake position closer to the center of pressure to reduce that moment created by the different air flaps around it. Another one would be to have more redundant and more robust recovery testing to account for any issues that we might have with it, and hopefully we would have been able to circumvent that issue where we lost our airframe due to the failed parachute deploy. And our last one would probably be having larger fins. Our issue with this year's rocket is that it had a very large pitching moment as it was going throughout the flight, and you can kind of see that in that onboard video and how it oscillates as it goes through. And the issue with that is it reduces the amount of energy we have that's throwing the rocket to its apogee, and instead is going into this rotation where it's slightly unstable. So in future iterations, we would of course have larger fins and maybe even a shorter rocket if possible. But with that being said, I hope you've enjoyed this video, and I hope you have a good day.